Right. You know, this English expression of changing gears. Normally, this is when you talk about something else, which I will do now. But I also feel like we're now changing gears because I'm just a lot slower than Letizia. But I'm really happy that that she was here. Really wonderful presentation, and yeah, she was a physics student here, so it's really nice to see where people go with the kind of things you learn here, but also in particular in you know, some of the very advanced work in machine learning that builds a lot on what you guys are learning in theoretical physics. So in particular, when it comes to building symmetry into your models and the like, lots of concepts from theoretical physics come back, and that maybe is a surprise at first sight, but not at second. Yeah, so I'm really happy for this constellation, or for the different things that the department can offer. And what I want to do is to complete the picture on what we have in generative AI. And you can fill a whole semester, of course, with generative AI, but I want to use the remainder of today and the next time we meet. And in generative AI, we have a variety of methods. Their main uses in science are, on the one hand, synthesis, so to create artificial. So you need a training set, of course, but then given this training set, you want to create, for example, fast-forward simulations, or you can try and infer the probability of an observation. So similar to kernel density estimation, just working better when your data becomes high dimensional or when it lives on special manifolds. And if you're able to evaluate the probability of an observation, this can be used for anomaly detection. And to give examples from the department here, this is, for example, what Jan Pawlowski is doing in his work in quantum field theory, or what Tilman Plain is doing in particle physics, where he's interested in developing algorithms that will allow finding outliers to hopefully find new physics. And this family of generative AI has many members, and I will, and they can have different qualities. Yeah, so one quality that you care about is so criteria for what is a good generative AI can be the quality of samples. And this is most obvious if you have generative AI that generates images, you know, how blurred or not these images are, or if it creates a person, how many fingers the person has, and all these things. Or you can be interested, of course, in the speed, the efficiency of creating new samples, or when it comes to this anomaly detection, there is the question of how easy it is to get probabilities out. So, okay, I'm going to write here fidelity. And by fidelity, this is a non-technical term, I mean how good are the probabilities that you can get out for observations. And important members of this family are diffusion models that we will talk about more next time. Then a bit outdated by now are GANs, or we have the class of autoregressive models. Autoregressive models. And we have just been hearing about them last time. The decoding kind of large language model like GPT. That would be an example of an autoregressive model, and a famous diffusion model that you have all used when you created images is Stable Diffusion, which was developed by Björn Ommer in Heidelberg just before he moved to Munich. Then there are energy-based models. Or EBM for short. They take some inspiration from physics. Because you try and model energy surfaces, the diffusion models also, by the way, we will see the diffusion equations, stochastic diffusion equations. This has a lot of inspiration from physics. Then there are the variational autoencoders. And finally, and what I want to talk about today, the flow-based models. All right, like I said, these generative adversarial networks, they're a bit outdated by now. They were all the rage maybe 3 years ago. So this whole field develops quickly. And I have now, I've given 3 criteria here. And what I've given here is now, well, I try to bring them into a linear order, which fails if we have 3 different criteria. But basically, the quality of samples is best up here. So in many applications, in particular, when it comes to generating images, diffusion models are best. And it is possible but difficult for these to get the probability of an observation out. So these are not very good kernel density estimators. And down here, what I called fidelity, so the ease and accuracy of getting probabilities. I'm just writing here good probabilities for observations. This tends to be best for those, in particular the last 2 models here. And it is for this reason that flow-based models are quite popular in the natural sciences. And I managed to connect this to the beamer, and it has then fallen asleep. Let's hope it does come back. Yes. And I want to start by giving you today a bit of an intuition. And these flow-based models, they have there's a lot of technicality. So what kind of, how to create invertible neural networks, etc. And this hides a little bit the basic idea. And the basic idea is not, so I thought I'd found a very clever way of explaining it. And then I was happy to see that this textbook by Prince, which I really like, and which I put further down on this page, that the textbook by Prince also has taken this perspective. Yeah? And I think it's easiest to explain in one dimension where coupling flows are not easily defined. Okay, so Starting with the very basics. I have here some probability density, and okay, so our headline is flow-based models. And I'm starting with a reminder of a few quantities. So in a flow-based model, we have some simple distribution, often a normal distribution, or a uniform distribution, so something we can easily sample from. And this could, for example, look like so. All right, this is our base distribution. And I'm here saying that it lives in a space with a which I'm going to call Z. And such a base distribution, it has a cumulative distribution function, so I can integrate from left to right. The cumulative distribution function at some value Z is the probability, if we say this is a random variable Z, that this random variable Z takes a value smaller than small z here. And for a normal distribution, so it always starts at 0, and then it goes to 1. And the inflection point is right at the maximum of this Gaussian. Okay, that would be the cumulative distribution function. And the CDF, so CDF or cumulative distribution function. And this cumulative distribution function has an inverse. So CDF to the -1 is also known as the quantile function. And this quantile function asks if we take, for example, the 50% quantile, so 0.5, where on the axis does that lie? And for the 25% quantile, I can ask where does that lie, and so on. And these quantiles, they are most densely spaced where I have the highest probability, and they have been marked here on this curve. Yeah? So what we see here are these quantiles. And by the way, I find it a bit surprising. If I look at this curve, I'm always misled by where they lie. So I'm pulling this down. If you ask me how much area is under this part of the curve versus how much area is under that part of the curve, I would have thought that this is bigger. But these quantiles are really equispaced. Yeah? So here I have 20 quantiles. And so each, between every two quantiles, there's 5% of the probability mass. All right, and this cumulative distribution function, because it's a nuisance to write CDF, it's often abbreviated with a capital F. And we indicate what random variable it pertains to. Okay, and now this was for the standard normal. And we can, of course, do the same for any other distribution. So here I have a complex distribution. It's a toy example. I created it as a mixture of two Gaussians. They have, I think, a probability of mass of 1/3 and of 2/3, and they have different standard deviations, as you can see. And here I can also indicate where the quantiles are. And this is now meant to represent the complex distribution that my observations have and which I want to model. All right, so now we have two distributions, and what I want basically is all right. What I want now is a mapping between my simple and my complicated distribution. So if I'm calling this axis here Z, and I'm calling this axis here X, then what I want is that X equals f of Z. So this is my mapping from one random variable to the other. If I had such a mapping, then I can go both ways. If I want to synthesize samples, I know how to draw samples from a standard normal distribution. I will just draw a sample from the standard normal, and then using my mapping, map it to the space of observations X, or vice versa. If an observation and want to know what is its probability, I can use the inverse mapping and then read off what has been its probability. All right, now this mapping, let's try and do that explicitly. So I wish I was taller, or maybe I can pull this a little down. Okay. So I'm copying here the locations of the quantiles, and I'm doing an okay job. More or less. And I'm also indicating the quantiles of this lower distribution. This one goes here, this one goes there. All right, and now our perfect mapping, I think it can be argued, should map one quantile to the other. So I'm using a different color for my perfect mapping. The first quantile maps to the first, the second to the second, the third to the third. So nothing interesting has happened so far. But just when it got interesting, I was missing out on more quantiles. All right. But the next quantile goes here, and the next one goes, and the next one goes there. Okay? And we can continue this. So this is my mapping here. This is X equals f of Z. You can think of it as a vector field or so. I could point in, I could make all of these as arrows and say this is a transport map. All right, and so if I have this transport map, as I said, I can easily generate samples. I will draw a sample from the normal, and then I will push it forward here through this transformation to get the real, or to get a sample in my observation space, and vice versa. If I want to know the probability of any sample, then I can push back. But in this pushing back, we need something else, namely, all right, let's take this point here. Yeah? If I just push it back, it looks like it has huge probability, but it should actually, here in this curve, it should actually have low probability. So we need to correct for this stretching or compression of space. Otherwise, we don't get out meaningful probabilities. And this brings me to my next picture. I think I will now try and continue here. All right. We see the same plot as previously, except I've now arranged them. And what we see and I've now plotted one quantile against the other. Indeed, so I take the location of the first quantile, I take the location of the second quantile, and unsurprisingly, this is known as a quantile-quantile plot. Which, by the way, is a result of programming by prompting. And so in this quantile-quantile plot, I have pairs of coordinates, and I take the cumulative distribution function of my first distribution, and use its inverse to find, for a given quantile Q, what coordinate do I find? And I do the same for the second distribution. So this plot here, I have pairs of points, and they are parameterized by my quantiles Q. So my quantiles Q, they go from 0 to 1. And this gives me the curve you see here. So the first quantile here maps like so, and the last quantile maps like so, and similarly for all others in between. And I was talking about this stretching and compression of space, and this is what we can see in this plot. So for example here, my QQ plot is very steep. So I'm trying to show a tangent here. So if I call this quantile-quantile plot, if I call this curve here small f, then the tangent that we have here is df by dz. Because this here was my axis label z. And so we have df by dz. And in this region here, df dz is large. And this df dz being large, it has values greater than 1. Okay, I'm just writing here larger than 1. Means that our base distribution gets stretched. Yeah, this is what we saw in the arrows before. My base distribution gets stretched. And vice versa, where it is flat, where it has a slope smaller than 1, my base distribution becomes compressed. And this is something that we can now take into account when we compute the density under the model. So for my model density, the density at some observation, I obtain it by considering the density from the base distribution, but now I must consider for this transformation, or we can think of it as a change of variables. And when we hear change of variables, we think Jacobian, and indeed this is what I need here. So I can take the derivative here of z with respect to z. It's taken at this location here. And now let's think about it. Should it become larger or smaller? So here the probability in x is actually quite low, and the probability in z was high, and I have a large slope. So I'm arguing qualitatively why I want something like the power of -1 here. And that's what we need actually. And so this part here corrects for the stretching or for the compression induced by my mapping. Because we start with a normalized probability distribution, we want to end with a normalized probability distribution, and so we need to take into account this stretching or compression. I also put absolute value here, even though the slope here is everywhere larger than 1. Do you have an idea why I used absolute values here? Okay, I will come back to this question of absolute value or not. And so now we have seen this plot, but what is this plot to do with this transformation here? Yeah? The connection is the following. In one dimension, and in one dimension only, unfortunately, this QQ plot or this function f, which I can obtain from it, gives the optimal assignment between the two distributions. All right, so we have two distributions, we have some assignment. What do I mean when I say optimal? And what I mean when I say optimal is in the sense of optimal transport. Now I've replaced one word by more words, but so what is this thing, optimal transport? I'm just curious, who has seen optimal transport before? Okay, it is a really fascinating topic and also important in machine learning. So in what is optimal transport, it looks at the cost of turning one distribution into another. And the most frequently used costs for optimal transport are the Wasserstein 1 and the Wasserstein 2 distance. And just like with the LP metric, you can define one for p equals 1 or 2 or other values. The Wasserstein distance 2 can be defined for other values, but Wasserstein 1 and 2 are the most important ones. So the Wasserstein 1 distance looks at any coupling or here what I will assume that the coupling is deterministic, and so I'm writing a transport plan instead. So we have a transport plan that takes us from Z to X. And we now look at how far we are moving mass and how much of it we are moving. All right, and then we're looking for the infimum here. The infimum goes over any transport plan. So we have here, we measure here, so this is the cost itself, and this is how much mass we are transporting. And I was saying deterministic, that's wrong. This, in this formulation here, it need not be deterministic. Yeah? This can be, this is any distribution living in this product space of Z and X, which has the right marginals. And this part itself here is the cost. Yeah? And in this case, it measures how far do we transport mass. And this is why it's also called the earth mover's distance. And the earth mover's distance, it is really this question of we have this one distribution, and we have the other one that you don't see because it's hidden. So we have these two distributions. We want to turn the first hill of mass or dirt into the second hill, and the cost of transporting mass is just given by the distance. Yeah? So if we transport 1 unit of mass by 1 meter, this costs us, let's say, €1. And so the question here in optimal transport is, what is the cheapest way of transporting to turn this hill into that hill? And the Wasserstein 2 distance, in contrast, penalizes transportation with the quadratic cost of the distance. So here we have the integral of x minus z squared and this is more akin to Euclidean distance, and the infimum here is taken in the same sense. Okay, so I was claiming that in one dimension, and in one dimension only, this QQ plot gives the optimal transport plan. So the claim is, no matter whether I'm using Wasserstein 1 or Wasserstein 2 or Wasserstein 3 or 4 distance, this prescription of where does each point from my base distribution go, that this prescription is the very best one I can possibly have. And so this allows me to, so that means in one dimension, we now know how to obtain a perfect transition from one distribution to the other. Now let's return to this question of why did we take the absolute value up there? This is a unique mapping, yeah. So it's 1 to 1 and onto. It's a bijection, but it also is a very smooth solution. Now, if we forget about optimal transport, can you think of a different way of transforming here one distribution into the other? So we had this mapping from one distribution to the other. Can you think of a different bijection? Yes? We could reverse, for example, part of the axis, or we can even revert the whole thing, because the Gaussian is symmetric. So this would be an equally valid mapping. Or rather than invert the whole Gaussian, I can decide to invert only parts of it. So for example, I could say between here and here, I'm going to invert. And here and there, I'm going to use the original one. So if we think of it as a transport map, here on the left-hand side, I'm doing what's reasonable. On the right-hand side, I'm doing what's reasonable. And in between, it crosses over. This is also a bijection, right? It's still a unique mapping. It's unique because for each z value, I have a unique x value and vice versa. It's still a bijection, but it's no longer smooth. So the first one was an example of a differentiable or a continuously differentiable mapping, what's also called a diffeomorphism. And this one now is a mere bijection. And only the first one was a solution to the optimal transport problem. But the second one, it's still a valid mapping. And this formula also works for the second mapping, where we decided to flip part of the distribution. And this is why I here need the magnitude of this derivative and not the derivative itself. Okay, so in summary, so far, what we have done is flow-based models in one dimension. And in one dimension, there's no need for neural networks because we've seen how to do it. Yeah, we built the QQ plot and we get a perfect mapping, and we can do synthesis and density estimation. It becomes more interesting now if our base distribution is not one-dimensional, but 100-dimensional, and our observations are not one-dimensional, but 100-dimensional. And it is at this point that we will need to learn this mapping with a neural network, and this we will do next time. See you soon. Bye-bye.